Welcome to this onboarding explainer, junior staff. Look, I am absolutely thrilled to have you join the team here, but before you even think about throwing on that pristine lab coat or touching a single beaker, we really need to break down the absolute golden rule of our lab. And honestly, it's the golden rule of modern chemistry as a whole. We're talking about the law of definite proportions. If you want to succeed in quantitative analysis here, and I know you do, this principle literally has to become second nature to you.
So, here's our agenda for today's briefing. 1. The core fundamental rule. 2. Meet Joseph Proust. 3. Real-world compound examples. 4. Verifying the law. 5. Compounds versus mixtures. And finally, number 6. Why this matters today.
All right, let's jump right into Section 1, the core fundamental rule, the unbreakable law. Consider this the absolute unbreakable law of the laboratory. It's our baseline assumption that dictates every single thing we do in quantitative chemical analysis. Here's the strict definition. A pure chemical compound always contains the exact same elements combined in the same fixed proportion by mass. Period. It totally doesn't matter where you sourced the sample, how you synthesized it, or how much of it is sitting there on your bench right now. Whether you have 10 grams or 10 tons, that internal mass ratio is absolutely locked in.
Moving right along to Section 2. Meet Joseph Proust, the architect. To really appreciate the pedigree of this non-negotiable rule, we have to look back at its origins. What's truly fascinating here is that this principle, which is also known as the law of constant composition, didn't just appear overnight. It was actually established way back in 1799 by the French chemist Joseph Proust. Just think about that for a second. Over 2 centuries ago, way before we had any of the advanced spectroscopy tools that we use in the lab today, Proust laid the very groundwork for modern chemistry. He proved that nature scales its recipes with perfect, unwavering mathematical precision.
Okay, let's see what that looks like in practice with Section 3, Real-World Compound Examples, the math in practice.
Let's take pure water, H2O for example. This is obviously our most universally handled solvent. Every single sample of pure water requires exactly 2 grams of hydrogen chemically combining with 16 grams of oxygen. Because of that specific combination, it locks in a rigid percentage composition, 11.1% hydrogen and 88.9% oxygen by mass. No exceptions, it never, ever varies.
And if we do a little math and simplify that 2 to 16 relationship, it means our mass ratio for hydrogen to oxygen in water is a strict, completely unchangeable 1 to 8. That's 1 part hydrogen for every 8 parts oxygen, strictly by mass.
You know, carbon dioxide follows that exact same logic. Whether it's being exhaled from your lungs right now or captured straight from a massive industrial chimney, pure CO2 always features 12 grams of carbon combined with 32 grams of oxygen. This creates a perfectly fixed 3 to 8 ratio by mass, which gives us a constant percentage composition of 27.3% carbon and 72.7% oxygen.
And let's look at standard table salt, sodium chloride. When you're measuring out NaCl at the bench, you are entirely relying on the fact that it always demands exactly 23 grams of sodium for every 35.5 grams of chlorine. That yields a guaranteed, fail-proof mass breakdown of 39.3% sodium and 60.7% chlorine. Honestly, junior staff, if your percentages don't match this exactly, you simply do not have pure sodium chloride. It's that simple.
Which brings us nicely to Section 4, verifying the law, data in the lab.
Because hey, theory is great, right? But as chemists, we live and die by experimental verification. How do we actually prove this when we scale up experiments? Take a close look at this data. Suppose 2 different laboratories prep pure water in distinct batches. Sample A is just a small 9-gram batch. Sample B is 90 grams. And sample C is a massive 180-gram batch. Notice how, even though the absolute component masses scale way up, from just 1 gram of hydrogen all the way to 20 grams in the biggest batch, the final mass ratio of hydrogen to oxygen stays at a perfect 1 to 8 across the board. The math always scales proportionately, always.
And this really brilliantly illustrates our foundational premise. Think about the massive scope of this reality. Whether that water comes from a rainstorm, a flowing river, the middle of the ocean, a deep-sea glacier, or is synthesized right here in a reaction vessel on your very own lab bench, that 1 to 8 ratio never changes. That rock-solid predictability, that's the bedrock of our entire profession.
Now, let's talk about where things can get tricky in Section 5,
Compounds versus mixtures, the crucial distinction.
As junior staff, this is exactly where you need to be exceptionally careful to avoid some of the most common fundamental lab errors. You absolutely must clearly distinguish between compounds and mixtures. Compounds, like the H2O and CO2 we just talked about, have a fixed composition. Their elements are chemically combined, and they rigidly obey the law of definite proportions. Mixtures, on the other hand, like the ambient air we're breathing, salt solutions, or soil, are just physically mixed. Their composition is highly variable. I mean, you can stir a little extra salt into a saltwater solution, and guess what? It's still salt water. Mixtures have absolutely no fixed chemical formula, and they definitely do not obey this law. Please, whatever you do not confuse the two when you're running your calculations.
And that leads us to our final section, Section 6, Why This Matters Today, Guardrails and Applications.
To wrap up today's orientation, we really need to make sure you understand the practical guardrails and the definitive applications of this rule in your daily tasks. Why do we care so much? Well, because this law is the absolute basis of stoichiometry. It's what allows us to determine precise chemical formulas with total confidence. It acts as our primary diagnostic tool to confirm a compound's fixed composition, easily distinguishing it from just a random mixture. Ultimately, it is the backbone for literally all the accurate quantitative chemical analysis you'll be running here. Without this law, all our lab data would just be meaningless noise.
But, as an analytical chemist, you also have to respect the guardrails. The biggest limitation is the one we just hammered home. This rule strictly applies only to pure chemical compounds. It completely falls apart when you're dealing with physical mixtures because their composition can, and trust me, will vary wildly. You simply cannot force a mixture to behave like a compound in your math. It won't work.
So, as you master these vital basics and gear up for your first assignments today, I want to leave you with a final, slightly more advanced thought just to keep you on your toes. The law of definite proportions is incredibly robust, sure, but what happens to our math when we start dealing with non-stoichiometric solids? Actually, certain metal oxides and minerals show these tiny, slight deviations in their mass ratios just because of minute structural crystal defects. So how will your analytical approach shift when nature decides to introduce a flaw into that perfect ratio? Think about that as you set up your workstations today. All right, that's all from me. Welcome to the lab, everyone.